Right. Hello, everyone. Thank you for making it out to our webinar this afternoon. My name is Daryl Saraspe, and I'll just be giving a brief introduction to SolWorks. But before I do so, I just want to make sure that everyone can hear me. So if you can hear me, please just use the screen to raise your hand. Good. Okay, perfect. So today we'll be having a webinar with one of our guest speakers, Dr. Mohammed Gamal. But before I do so, I'll just give a very brief presentation on our software for geotechnical engineers called SolWorks. Okay, so here's just a brief overview of what I'll be going over. First and foremost, I'll just be going over our company, Midas, what it is we do, and a little bit of our history. So our software is developed by engineers for engineers. This is very important to us because we, as an engineering firm, have great experience in understanding the needs of engineers around the world, especially when it comes to software. So our specialty is giving engineers the tools they need in order to work faster and more efficiently. So we have several other software programs in the market right now in addition to SolWorks. Some of them include Midas GTS for 3D geotechnical design and analysis, Midas Gen for building and general structures, Midas Civil for bridge and civil structures, Midas FEA for advanced nonlinear structures, and Midas NFX for mechanical engineering. Okay, so our company was founded about 20 years ago, but within that short time frame, we've been able to establish a worldwide network. So hundreds of thousands of engineers around the world are currently using our software, and it's a very powerful tool for them. They've been able to increase the efficiency of their work, save much time and money. Okay, so we pride ourselves on being total solutions providers. Any types of problems or projects that engineers face, our software provides solutions. We have world-leading technology. Our software is used by leading firms around the world for landmark projects. The imagination to creation, our software provides the tools to make engineers' visions a reality. And of course, our global network. By becoming a Midas user, you join a network of engineers that are using the software and supporting each other. We analyze and design the future. Our software is used for projects that create a better world, a better tomorrow. Okay, so I mentioned that we have like a lot of industry-leading companies that use our software, and they've used our software for many landmark projects. For example, the King's Cross Station in England was analyzed and designed using Midas GTS. Also, the Dubai Tower in Qatar, the Pile Raft Foundation was also designed and analyzed using Midas GTS. And then the Russky Island Bridge in Russia, currently the world's longest and tallest cable-stayed bridge, was designed using Midas Civil. And then the Burj Khalifa Tower, currently the world's tallest building, was analyzed and modeled with Midas Gen. Okay, so now I'll talk a little bit about SolWorks, and I'll give like a brief introduction to it. So SolWorks, it's an all-in-one software package that's been designed to handle any type of 2D geotechnical project that you may encounter, and it's separated into 6 different modules. So this video briefly touches upon each module, and I'll just go over the main features. Okay, so there's the tunnel module for your tunnel design and analysis, also your general FEM modeling. You can also use it for excavation projects. And as you can see, you can get the effects of excavation on local structures. The slope module for cut and embanked slopes. A great feature of this module is you can perform FEM and LRM analysis simultaneously. You can also check your reinforcements. The soft ground module for settlement. You can analyze the settlement of a clay soil over a long period of time. You can also analyze the immediate settlement of sandy or siltier soils. Then the foundation module for PY analysis of your pier configurations. You can model multiple pier configurations simultaneously and immediately get your results. And then the seepage module to analyze the effects of seepage on your soil interaction or your foundations. This is often used for dams and levee analysis, but you can also use it in coupled analysis with a slope module. And then last, the dynamic module for your seismic analysis. The program has a database of history records for earthquakes, so you can get a very accurate simulation of an earthquake in the area in which your project is involved. So those are just the 6 modules. As you can see, any type of project that you might face can be sort of handled with this software. It's an all-in-one package. Okay, so one of the main things to remember about SolWorks is that it's very fast. As you can see, we've created 7 innovative smart features to help cut down on the time it takes to perform your modeling and your analysis. So this primarily focuses on eliminating repetitive processes and then also reducing the number of steps it takes you to complete your projects. Okay, so the best way to really demonstrate how fast SoilWorks is just to give a demonstration. So in the following video, what we'll be watching is a user using SoilWorks to model and analyze a tunnel project. And as he does so, he'll be using several of these smart features, and I'll just be touching over each one as we watch. Okay. So first, he'll just choose the tunnel module, because obviously this is a tunnel project. Afterwards, he'll define his units. As you can see, we have a broad list of options for your units. Everything's included. Next, he will be importing his AutoCAD file. So instead of having to, draw your model on the program, you can just import it directly. So within a few seconds, your drawing is set. Next, he'll be assigning ground material properties. As you can see, we have an extensive database of ground materials that you can intuitively choose from, and each material comes with its various properties. And if it isn't included, you can just input it in the database. And then structural properties. We also have an extensive database of various structures, their properties, and then section shapes and types for any kind of element that you'll be using. And then smart surfacing feature that allows you to just intuitively separate your surfaces, and then as you can see, the user is simply dragging and dropping the material and structural properties onto the drawing. And then the smart mesh feature, within a couple of mouse clicks, you can have your meshing set for you, along with all of your mesh sets in the work window. Next, he'll be applying his pressures. So for this particular project, he'll be applying a distributed load just right over the tunnel to represent traffic. And the Smart Support feature allows you to just intuitively set your boundary conditions. And then changing attribute. This feature allows the user to just change the attributes of various materials over a certain period of time. So for example, this will be a construction stage analysis, so the attributes of the foundations will be changed, and that's what the user is assigning. Then construction stages. So for construction stage analysis, as you can see, you can easily just sort of format your construction stages, and then you can also define which elements will be present during each construction stage, so that you can get a very accurate simulation of the changes that takes place over the course of the excavation or the construction. Okay, next he'll be defining his analysis cases. So this will be a tunnel project with a structure check, and he's just defining all of his properties. And then design options. So he'll be specifying obviously his options for design. So he'll be just assigning the allowable displacements for the elements and also the allowable shear stress. And then tunnel members. This allows you to sort of group elements that you'd like to see analyzed together. So in this particular project, he'll be choosing the rock bolts just to be sort of analyzed together in the final report. So in that way, instead of having to extract the results from a large spreadsheet, they'll all just be grouped together for him. And then finally, he'll be performing his analysis. So within a few seconds, you're in post-processing, and all of your results are easily formatted and laid out for you. And you have your contour tables representing your various displacements, deformations, etc. And then the rock bolts and the crown members are grouped together so that in the final report, it's all very easily formatted for you for your convenience. So in about 3 minutes, he was able to finish everything. Obviously, that was an idealized example. But that just goes to show how quickly you can perform your modeling and your analysis with SoilWorks. Okay. So next we'll just talk about some of the key features of SoilWorks. Smart meshing, as you saw in the video, the user is able to immediately create his meshing using the smart mesh method. That being said, these other options are available to you. And then you can easily create models without FEA knowledge. So as I said, we have a large database of various material types and properties that you can use for your projects. Simple analysis. So the software allows you to perform your analysis without having a very in-depth knowledge of it. So all of these analysis types are available to you. With a simple click of a button, the software will perform the analysis for you so you can just focus on results. And then SoilWorks is very affordable. So as I said before, it's a 6-in-1 sort of software. So all these 6 modules come in the package. So for example, you won't have to worry about purchasing any outside software. A lot of geotechnical companies, they have several software packages to handle their various applications. But with SoilWorks, you just get one all-inclusive package at a very competitive price. So those are the main things to remember about SoilWorks. These are the main benefits. First and foremost, it's fast because of its 7 smart features, which we just discussed. It's easy. Any engineer can use it. It's very user-friendly. It has a very soft learning curve, and also we provide free training and free technical support. And it's affordable because it's a 6-in-1 software. It streamlines all of your work, so you only need one software package. Okay. So I'll just go into a few in-depth design features now. So currently, for example, with tunneling, there's an 8-step process that exists because of construction stage analysis. The engineers often have an iterative process here in steps 4 and 5. But with SoilWorks, we're able to itemize or to sort of streamline the work so that multiple files can instead be, or multiple cases, excuse me, can be analyzed in a single file, thus greatly reducing the time it takes to perform parametric studies. Also, the auto report generation feature allows you to immediately just generate your report through the software. So instead of having to extract the results and format them, the software just does that for you within a matter of minutes. Okay, CAD modeling features. Another great feature of the software is that if you can use CAD, you can easily use SoilWorks to model your drawings or your projects. So all of these commands should look familiar. So if you're familiar with CAD, you can easily just use SoilWorks to do all your modeling. As I said, smart meshing allows you to just intuitively create your mesh, but if at any time you need to do auto, map, or grid meshing, these options are available to you. Boundary conditions, as you saw in the video, boundary conditions can be created very intuitively. And load types. The software includes all load types that you could possibly need for your projects. Design results. This allows you, once again, to group your analysis. So for example, if you have certain structures or certain sets of elements that you'd like to see grouped together, you can intuitively choose those to be printed in your final report. As you can see, the final report is very clean. It's very easy to read. Everything's formatted for you. Your charts, your graphs, etc., and even a table of contents will be created for you through the auto report generation feature. And then you also have a wide range of graphical results to choose from, so depending on a personal preference, you can choose from various contours and graphs to include in your final report. And then tabular results. All of your results are formatted in Excel format, and it's all included in the post-processing. So instead of having to create the graphs yourself through an Excel sheet, the program will create it for you. Okay, so in the interest of time, I'll just speed to our conclusion. Project application. So here are just a few projects that our software has been used for. Mountain tunnels, as you can see, the software can very intuitively sort of analyze the effects of the soil because of excavation. Tunnels with temporary structures, so the tunnel module can also be used for excavation projects. Subway tunnels, as you can see, the effects of adjacent structures are being analyzed through that contour graph. Reinforcements for cut slopes, so you can very intuitively compare the effects your reinforcements will have on your slopes. You can also check for dry and rainy seasons using coupled analysis with the seepage module. Slope stability at a tunnel exit. Reinforced earth retaining walls. This is another feature that, or this is another type of project that the slope module can handle for you. Stability of a piled raft foundation. Obviously using the foundation module. Abutments on slopes with and without pile effects. So once again, you can intuitively just compare the effects your piles will have on your slope. Group pile behavior, another function of the foundation module. Settlement in soft ground. Obviously, this is for the soft ground module, so you can analyze your consolidation of clay soils over an extended period of time. Dams and levees with cutoff walls. You can analyze the effects of seepage on your dams and your levees. And underground structures. Once again, the tunnel module allows you to analyze these. Okay, thank you for your time and attention. If you have any questions at all about the software, feel free to send me an email, dsaraspe@midasuser.com. And my name is Daryl Saraspe. I'm just a CAE consultant here at MIDASoft. Okay, so now we'll get into Dr. Gamal's presentation. So I'd just like to very quickly introduce him. So Dr. Mohammed Gamal is a senior geotechnical engineer and project manager at Brierley Associates. He received his Bachelor of Science in Civil Engineering in Egypt, and he received his Master's and his PhD in the University of Illinois, Urbana-Champaign in geotechnical and transportation engineering. He's had extensive experience in different geotechnical projects, and today he will be presenting the use of a vertical shaft machine for excavating deep shafts, which is a new method in excavation. Okay, Dr. Gamal, you may start.
Okay. Good afternoon, everybody. Before I start, does everybody see the screen right now? Can raise your hand. Okay. Today I will discuss a new construction technique that was used for the first time in the US for the construction of a 150 feet deep shaft. It was a launching shaft for a siphon. It's a sewer siphon. And during the course of this presentation, I will start by giving a brief background about the project, and then I will move on to give an idea about the geotechnical conditions at the launching shaft site. Then I will cover the different construction alternatives that were allowed by the owner for that specific location. Then I will describe the vertical shaft machine and the different components of the machine and how it works. And finally, I'm going to cover or briefly cover some of the design considerations. And the idea here is not really to give a step-by-step design procedure, but it's more to emphasize the importance of considering the soil-structure interaction and how can you save, or you can use very little steel or reinforcement when you take that into consideration. The need for this project started by the growing need of the Kings County in Seattle, Washington, in the wastewater treatment division. And the idea was to replace two 36-inch wooden pipes that were built in the 1930s, and that, as you see here in the schematic, the two pipes went under the Salmon Bay in Seattle, Washington. And as you see here in the plan view, the construction will involve building two shafts, a launching shaft at the south end of the Salmon Bay, and then there is a retrieval shaft at the north end of the north side of the Salmon Bay. The VSM was used for the launching shaft, and the secant pile system or support system was used for the retrieval shaft. The launching shaft was significantly deeper than the retrieval shaft. The depth of the launching shaft is about 150 feet deep, and for the retrieval it was about 85 or 90 feet. And so basically the idea is to replace the two 36-inch wooden pipes by an 84-inch pipe, and after building this pipe they are going to go back and clean and reline or use a new liner for the existing 36-inch pipes and add it to the system later on. Next, I will cover the geotechnical condition at the site. So what we have here is about 8 foot of what's called the Holocene fill. And this is mainly a sandy and silty fine to coarse gravel, with coarse gravel and medium stiff clay. Then you have 10 foot of what's called Vashon outwash, and this is medium dense and fine to medium sand with fine gravel, and it has some cobbles and boulders. And this is followed by about 70 feet of what's called the pre-fraser deposits, and this is mainly a very stiff to hard clay, and also has some underbeds of medium dense to very dense sand. And again, it has some cobbles and boulders and in that formation. Then all these layers are underlain by what's called the pre-fraser slicken-sided deposits, and these are very hard clays, and it has some fissures or fractures which are filled with sand. And in that formation, the in situ stresses are significantly high, and based on some in situ measurements, the K node values ranged from about 1.6 up to 3, even though I doubt the 3 thing, but that's what was measured in the field. I would imagine it's more like 1.6 to 2, 2.5 at most. So these are basically the geotechnical condition at this site, at the launching shaft site. Two main concerns, if we're looking at this formations, the two main concerns are the existence of the cobbles and boulders at the site. This is one issue, and the other issue is the very hard clay at the very bottom of the shaft, near the bottom of the shaft. And if you run some numbers, you will see that if you have undrained shear strength of about 4,000 BSF, you will end up with a bearing capacity of about 20,000 BSF, and that corresponds to a concrete column of 135 feet. So keeping in mind that actually what we have here, the undrained shear strength of about 10,000 BSF or more, so you can imagine it will be very hard to sink this shaft using a regular technique of sinking shafts. And so we have to come up with a new or another alternative to build this shaft. According to the pre-bid documents, and the bid document, actually, the owner allowed 3 different techniques for building the shaft. The first one is using caissons, and the other one is to use a slurry wall system, and finally the use of ground freezing. And they will cover the shortcomings of each of these systems. For a caisson, it's really hard to, if you have 148 or 150 feet deep shaft, it will be hard to keep the verticality or to keep it level during the course of construction. In fact, once you exceed about 90 to 100 feet, you end up with some problem keeping the verticality of the shaft, especially if you hit boulders and high in situ stresses, as in our case. Which again, as I said here, as shown here, the high in situ stresses it creates a high potential for the shaft to get stuck and have some problems trying to sinking or advance the shaft into the soil. And again, as I described earlier, the existence of boulders and cobbles, this can actually, in some cases, can damage the shoe and again hinder the progress of building the shaft. And for this system, you'll end up with a relatively thicker liner compared to the VSM or the vertical shaft machine system, which I will describe later, where we use only 15-inch thick liner or segments. The second alternative is the use of slurry wall system using a digger or a hydro mill. And again, we'll end up with a thicker liner. And also, if you apply the ACI 350 code, you will end up with significant amount of reinforcement that's needed in the segments. And also, this system uses a larger, space to have the system set up, and it's expensive compared to the system which I'm going to discuss. And the other issue, if you have cobbles or boulders, you end up with what we call windows in the wall. So you end up, some of the boulders may come into the slurry or the concrete after you pour it. So you end up with some windows in the wall itself. The last item is the ground, or the last alternative is the ground freezing. And if you start using ground freezing, it's very expensive and time-consuming process. And And one serious problem or concern is the potential for eroding the freeze wall. So basically, and this I will describe one case history here when you can end up actually collapsing or failing the whole shaft because if you start eroding the freeze wall. And the other issue is you should always keep a reasonable rate of advance of the TBM during the course of the project, especially near the shaft itself. There was one case history where the TBM broke shortly after the breakthrough near the shaft, and it took 3 days to fix the TBM. And when the contractor tried to advance the TBM, he couldn't, and the TBM was actually frozen in place. And when you start heating the TBM, trying to unthaw, or thaw the freeze or the ice around the machine, eventually he developed or eroded the wall or the freeze wall, and the water started rushing into the shaft. In fact, the whole shaft collapsed and failed. And other issues, you have to keep this system running all the time throughout the construction process of the shaft. This picture, as I described earlier, the concern about having very high in situ stresses. This was one case history which I worked on, where the contractor was building a 150 feet diameter shaft, and when he started hitting the very hard clay at the bottom at about 55 to 60 feet, he started having serious problem trying to advance the shaft. And as I described earlier, you can imagine the very high bearing capacity of the soil at this depth. And what happened, as you see here on the right picture, you can see here that the cracks start propagating from the bottom all the way up. And you can imagine that this wall actually is like 7 foot thick. So it's like 7 feet of concrete were destroyed when the contractor hit this very hard in situ stresses, or very hard clay with very high in situ stresses. The K naught here for this case was about 1.2 to 1.4. So the ratio of the horizontal stress to the vertical stress was 1.2 to 1.4. So in our case, actually, the ratio was 1.6 up to 2 or 2.5 maybe. So, and as you see here, this is actually on the left, it shows the picture of the shaft, and this is on the right, you see a picture from showing the inside from the inside of the shaft, where you see all these cracks propagating, and they started from the bottom up. Next, I'm going to describe the vertical shaft machine and the different components of the machine. And the machine basically has 3 main components. It has a sinking unit, and what we call the shaft boring machine unit, and a separation plant. And for the separation plant, you need this if you are working in the wet. I mean, so because as I said, this machine actually you can use in the dry or in the wet, so you can excavate in both modes. The sinking unit has 3 or 4 more components. First of all, you have 3 to 4 winches and jacks at the ground surface. Each jack has a capacity of 300 to 500 ton. And then you have a massive ring beam at the top to support the jacks and the winches at the top. And this ring beam actually is not connected to the shaft, so it's a separate unit from the shaft, but surrounds the shaft. And then you have what's called the steel strands, or cable basically, and black boxes in which support, the steel strands are actually fixed into these black boxes. And I will show some drawings to explain all these components. The main purpose of the sinking unit is to keep the shaft level at all times. And so basically, using the sinking unit, you will be able to suspend the whole shaft all the time during the construction, then let it sink as you excavate below. This is a drawing showing the sinking unit components, the upper part of the sinking unit. And as you see here, you have a group of jacks and winches, which basically are used to either suspend the jack in place, or the shaft in place, or actually can also push against the shaft if you need to. And if you look in the drawing, you will see some red lines coming through the jacks here, or the winches, it's like almost like crane. Basically, you suspend the whole thing in place. So you see all these red lines. Actually, the red lines that goes down, this shows all the cables or the steel strands that goes all the way to the bottom. And here you can see the segments. So we have here each ring of the shaft has like 4 segments, and these are 15-inch thick prefabricated fiber reinforced concrete segments. So as you see here, each ring has like 4 segments here. The next drawing shows actually the lower part of the sinking unit, and if you look here, there is a small box here, 4 of them actually, and these boxes houses, or in fact the cables are attached to these boxes. The steel cables or strands are attached to this cable at the very bottom, and they are fixed in place. So basically you start by putting these boxes, and this is ring number 1. So this is the first ring that you build. Then as you excavate below this ring, you start adding more rings. So you go ring 1, 2, 3, and so on, all the way to the top as you see here in the previous drawing. So you reach all the way to ring number 58. So you can see as the shaft can always be suspended during the construction process here. Here, this is a photo showing what I'm talking about. So you can see here, this is the ring beam I was talking about, which support the winches and jacks at the top. And you can see here there's a 20 steel strands coming through the crane, and they go through the first ring, okay? And you can see on the left photo how they attach the steel strands, or they are wedged actually in place into this plate, and this plate will eventually go into this hole here, into this opening, and you do the same thing at 3 other locations, so you can actually suspend this ring and all other rings that will come on the top of this ring in place during construction. So each, as I said, like these are about 20 cables here. They go through this ring. So they come from the outer side here, and they go through into what's called the black boxes, which I described earlier. So this is actually, if we go to the previous drawing, these are actually the boxes. They call them the black boxes. I don't know why, but this is where they attach the strands basically. The second part of the VSM, or the vertical shaft machine, is the shaft boring machine. And you can look at it, it's almost like a road header actually, boom. And it has a rotary grinder, and you can fit it with different or special cutting discs. And that, according to, depending on the soil condition or the soft rock, you can fit it with different discs configuration. And the arm, or the road header has a telescoping arm. So actually, and as I will show later, you can actually over excavate or under excavate under the segments as you advance the shaft. And as I described or said earlier, you can actually use it in the wet or in the dry during construction. Here, this is a plan view showing the shaft boring machine, and you can see here, this is the rotary grinder, or the drum actually, which cuts into the soil. And you can see actually you end up suspending this machine. It's about 80-ton shaft boring machine, and you suspend it from 3 at 3, legs basically to the segments from inside using a bracket or some plates, attached to the side of the rings. So you see here there's 3 legs, and you have here a telescoping arm, which are used to cut the soil. And again, remember that this shaft actually is connected to the very top. So you can see that actually the shaft boring machine is independent of the sinking unit. So they are 2 separate systems. They are not attached to each other. Of course, there is some controls that goes to the control unit, but you can see they are independent. Finally, this is a separation plant. This is a photo showing a separation plant in action. And basically, you will start collecting all the granular size, the byproduct of excavation, and you using a system of hoses that's actually integrated into the shaft boring machine itself or the drum. And you can remove this when you are done. And you can see also in this photo how the rings are stacked on the top of each other. So as you excavate, this thing will keep sinking as the machine continues to excavate. Finally, I'm going to briefly cover the design consideration here. And as I said, the idea is not really to give a step-by-step design procedure, but it's more to show that actually you don't need much reinforcement if you consider the soil structure interaction, as I will show in the next few slides. The first item is the cutting ring shoe, and actually this is a critical ring because actually this thing supports the whole shaft and also can be used for or jacked into the ground to cut into the soil if you have to. And as you see here, if you look at to the left, the drawing shows that actually you have like a 2-inch protrusion behind the cutting ring segment. So you have almost, as you push this ring into the ground, you will have a gap of about 2 inches between the ring and the soil, basically. Eventually, this thing will close in as you go deeper, but initially you will need this gap so you can easily advance the shaft or this cutting shoe ring. So first of all, you design this thing, you need to consider the full passive resistance, so you can develop this the helical, passive wedge basically, and you start analyzing the forces which comes perpendicular to this side here, and you can come up with some reinforcement to resist the moment and shear at this plane. And the second thing, you need to look at the earth pressure and check buckling, earth pressure and water pressure if you have water. And then you need also one other concern or design concern is the significant shear at the shear box or the black boxes location. You remember we've shown like 4 black boxes where you attach all the steel strands, and so we end up actually welding some steel bars to these boxes so you can have better distribution of the shear at this location. And as you see here, really you don't have much, not very heavy reinforcement. All you see is like number 6 longitudinal bar, or actually ties, and some circumferential reinforcement is like number 4. So it's not really a very heavy reinforcement. And again, that's because you take into consideration the soil structure interaction, so you don't have to use really very heavy reinforcement here. And that's actually the main point of discussing this, that you don't need too much reinforcement. And also another other consideration is like to check the bearing stresses at the top of the segments, especially the cutting ring segment, because of all these cuts into you have these grooves to house. This is actually a tie rod, which eventually you keep tying all the segments together by having rods that go through all the segments all the way to the bottom. So the whole system is connected together using these tie rods that goes into the middle of the segments at specific locations. So, and because of the relatively thin, you need to check the bearing stresses at the top of the segments and at the bottom, of course, of the other segments. And as I described earlier, these are fiber reinforcement, but the fiber reinforced segments, but we have to use additional regular reinforcement to take into consideration the higher stresses for some of these segments, specifically the cutting ring segments, and next the shaft boring machine support rings. You remember I showed before, let me go back very quick here. As you see here, the boring machine is attached by these three legs via some bracket or some blades, steel blades are attached to, actually two segments will do that, like segment number 3, if I go back to the, you see actually the shaft was, the boring machine was attached to ring number 3 and to ring number 5. Actually, these are the two rings that the blades went through them, across them, to support the 80-ton vertical shaft machine here. And so the main design consideration for this two rings is to consider the torsion, because the load is applied at the edge via blades, via the steel blades. So you need to design it for torsion, and also you need to look again at the forces coming from the earth and water pressure, and also check again the bearing stresses, and this is always a concern because of the relatively thin segments here. But again, you see here actually you don't end up with heavy reinforcement. It's like you have 6 number 4 longitudinal bars or circumferential. It goes across the perimeter of the segments, and you have, and these are basically longitudinal bar to resist the torsion. And in addition to the ties, of course, you have number 4 ties, and they are spaced like 8 to 12 inches, you know, depending on the location of the of these ties. And finally, the other component is the surface ring beam, which I described before. It's a huge beam, and it's used to support all the winches and jacks at the very top. And as you see here in the schematic, you see that actually the forces are applied very close to the edge. They are not centric, but they are, because of the construction issue, you have to have the cranes very close to the edge, so you can put in your cables and stuff like that and attach to the rings. And this creates, of course, you need to look at the soil structure interaction. Again, I modeled this using a program, SMAP, to look at the net torsion and the other forces acting on the beam. So I'm not going to get into all the details of this, but basically this shows, you know, some of the forces acting on the ring beam here. The other item which I would like to cover, which is not shown in the presentation here, is the trim slab at the bottom. The beauty of using this vertical shaft machine, that you are able to control the shape of the excavation at the bottom. So what we did, we have like an arched shape, or like an inverted dome, basically like a dome, but it's an inverted dome. So the shape is more like, rather than having a plain slab, you have more like curved slab at the bottom, trim slab, and this significantly reduced the moment. And in fact, we didn't need any reinforcement at the bottom for this trim slab. It was about 10-foot thick trim slab, and the construction is done, and it's holding still, and it's working fine. And we're getting ready actually for the breakthrough next. Finally, so looking at this system, you can see the main advantages of using the VSM machine or the vertical shaft machine. It's very cost effective, and in fact, I didn't discuss it here, but you can achieve easily between 7 up to 15 feet of rate of advance a day, and the day was like 10 hours a day, you know, so it's 10 hours per day. You can easily advance at about 7 to 15 feet, up to 15 feet a day. And of course, there is a learning curve in the beginning. As I said, this was used for the first time, but eventually, in some cases, they were able to achieve 15 feet a day at rate of advance. And the system worked, as I said, in the dry and wet, so no need for dewatering, which was a concern here because actually the water or the groundwater at this site was polluted. So no dewatering at this site. And this system can work in electric power. So you don't have as much noise as diesel engine. So, and this is critical if you are working in the city or in any urban, you know, location. So, and also, as I said earlier, that the footprint of this system is like the setup is really small. It doesn't take a huge space to set up the system. And one other important aspect is the ability to excavate under the toe of the shaft, and by using the sinking unit system at the top, you can easily control and keep the shaft level at all times, so you don't have tilt or out of plumbness, you know, issues with when you are building it. And the other, of course, one of the very critical or important issue is the ability or the control of the final or the quality of the liner. You end up always with an excellent liner because this is a prefabricated unit, so you know what you are putting into the ground beforehand, so you don't have, unlike other systems like seek and pile or diaphragm wall, you cannot really guarantee you end up with a good quality product at the very end. But here, you know, you are putting this liner in place and you know what you are getting at the very end. This concludes my presentation, and I'd like to thank you all for your time. And now I will check to see if anybody has questions, so I'll be happy to answer them. Check the questions here. Hey, Buya, could you, here's the questions, okay. Okay, I will go through the questions very quick. Yes, the first question, somebody asked if we can use this for rock. You can use it actually for soft rock. And there was one instance, actually they use it in a medium to hard rock, but it's mostly used for soil and soft rock. But actually now they developed recently a system which can be used in rock, medium to hard rock. And the second question is, oh yeah, this system have been used in Europe. Somebody's asking how many VSM has been used in abroad. I don't know exact number, but I know for a fact that was used in Europe, and that about 4 to 5 years ago, this system started being used in Europe and some area in the Middle East too. So but this is what actually it was the first time to be used here in the US here. Somebody asked what was the diameter of the shaft. The shaft diameter was about 32 feet. This is the outer diameter. And this thing I read one case history, but I need to confirm this. It was in Moscow that actually they built the shaft was about 150 feet in diameter. But again, I need to confirm because I heard this and I need to confirm. Somebody asked, it was not obvious to me how would water coming from the bottom would be handled. Could you explain, please? Yeah, somebody asked how water will be handled coming from the bottom will be handled. In fact, as I said here, that you are building it in the wet, so you actually fill the shaft with water to balance the water pressure, and then at the very end, when you reach the desired depth, you start by pouring your trim slab concrete. And as I said, that I will go here back to one of the drawings very quick. You can you can actually use, this is the outer diameter here, as you can see the outer diameter. Actually, using this telescoping arm, you can actually over excavate. So in fact, we ended up with 1 foot over cutting. So you have an extra 1 foot outside the outer diameter using this telescoping arm of the grinding head. So you can actually, your trim slab can extend away from the shaft perimeter about 1 foot or so, and then once you keep, of course, you do all this underwater. You put your trim slab and everything underwater, and eventually when it hardens and reaches the desired strength, which was about for this case, it was about 4,000 psi concrete strength. When it reached the strength, you can actually start dewatering and removing the water from inside the shaft. So this is how you handle water into the shaft. I think, yeah, one person asked about the rate of advance. I think I covered this. It can be, as I said, it ranged from about, for this project was about, an average was about 8 feet, and you can achieve up to 15 feet a day. Yeah, somebody here asked about the cost effective. I would like to say here that even though contractors are really very sensitive, the contractor for this project was GW Fowler, and the machine is from Heron Connect, and they don't really discuss all this cost issues, but I can say it's cost effective, and in this case with a combination of using a smaller shaft than the initially proposed and using this machine, the total saving was about 50%. But again, that wasn't combined with the using of a smaller shaft too. So this is about the cost. Yeah, somebody asked how did you measure K0 value? That was done by one firm, and they used the pressure meter test. And yeah, about how reliable the measurements, as I said, it will give you a feel. I cannot say it's 100% reliable. There is always some issues with the pressure meter test, but you can always get a feel, or at least calibrate it against area which at the top you can compare at least the ratio of or look at the values of the K0. So, but yeah, I mean, as I said, for me it was hard to believe it was up to 3. This is hard because actually, unless you are very close to the rock, but for me the more reasonable value was like 1.5 at most, 1.6. You know, I don't expect it will be higher than this unless you are very close to bottom rock, or the bedrock basically. Yeah, there was one other question about what kind of separation plant was used. It's almost like a slurry system, and I'm not really, I don't have good background or strong background about the separation plant. I was not involved in that, but it's processing like what looks like a slurry system, almost like slurry system. Yeah, I think another question is who is the machine manufacturer or developer? It's Heron Connect, and this is in Germany. What would be the shaft diameter range with the VSM? I think I covered this. I think there's a lot of cases covering between 30 feet all the way to 40 and 50 feet. And as I said, except one case in Moscow, which I read in one web page, which was up to 150 feet. And again, I need to confirm this, but I read it on one website. And that was in Moscow, actually. One other question: as the shaft is sunk down, are the strands and black boxes holding up the weight of all segments? Do you have some more slides on it? Yes, in fact, throughout the construction process, the shaft can be held in place through all the time if you want to. And as I said, you let it go when you are done with a certain interval and you are ready. You advance it one ring at a time. Each ring was like 1 meter high, which is about 3.28 feet high ring. So each time you let it sink and you advance it slowly, basically. But yes, the black boxes and strands can suspend the whole shaft in place if needed. And that's what you design the ring beam and everything for. And that's how you rate your cranes or the winches and the jacks. Is it easy to facilitate an opening to connect your other structure? Yes, actually this system doesn't interfere with any subsequent construction. Like if you start the breakthrough process or so, it doesn't really interfere. Once you are done, you remove everything. You will take the shaft boring machine here, you can take it out and you remove everything, and in fact at the very end you cut the strands which suspend the shaft in place. You don't need it. So basically when the trim slab hardened, you can just let it go and you cut it at the very top, and eventually you remove all this system and you start lowering your TBM machine down the shaft and you start the breakthrough through the segments. Of course, there is certain special design at the breakthrough in addition to the segments, because the segments themselves wouldn't be able to support, the forces induced by the moment and shear, induced by the cutting of the breakthrough by the TBM. Yes, I think I answered this question about one gentleman asked if I have to, in order to account for the TBM breakout, were special shaft rings used? Yes, as I said, we have to use, in this case, you cannot actually change the rings. I mean, you use the same rings all the way through. You cannot change, put like 15-inch and after that you put another 20-inch thick, segments. You cannot do that. But what we did, we have to add like cast-in-place slab around the area of the breakout or the launching the TBM. So this is a special or a separate design. So we have to design an additional wall so you can have enough resistance or strength to resist the induced forces. Actually, the cast-in-place wall is it took almost one-fourth of the perimeter to build. So you have an additional, I think it was more like 20-inch additional, wall, in addition to a steel frame, which also embedded into this cast-in-place concrete wall, in addition to these segments, to account for the TBM forces and the breakout. Oh, one person asked about the crew size. Actually, the crew, it's highly automated, and in fact, it's all operated without even seeing the boring machines. It's all underwater. And if you look at the operating room, it's almost like a spaceship. Actually, and it's also like two people actually were operating the thing from the ground service. But of course, there is some other people who will keep track of cleaning, the separation plant, and of course, putting the segments together and the rings and all this stuff. Another question about the diameter of shaft, and I covered that. It's 32 feet outer diameter. Yes, actually, is the as constructed shaft watertight? Actually, it was excellent, and actually we didn't have, except very few drips. And which I didn't discuss here, that actually between each segment, as I said, like each ring has like 4 segments, and there is gaskets, to keep water out, and there is a special design which I didn't cover here for the gasket to guarantee, that under different pressure conditions that you wouldn't have any leak. And I would love to show a picture, but actually I can, the person who's interested, I can send him a picture. He can send me an email, and I will send him a photo for the final product, which I got like a couple of days ago. And you can see it's working very well. Very few drips, coming out. Is it possible to a shaft geometry such as an ellipse? I'm not sure about that. Mostly it was used to build a circular shape shaft. But I will check, and I will forward the answer to. Yeah, please send me an email so I can respond to you, and I'll ask the contractor and come back to you with an answer if we can build an ellipse, for instance. There is another question about if the shaft annulus was grouted from the surface of the segment boards. Yes, actually, what you do here in these segments. Let me see if I can. I think you can see it in one of the picture. In these segments, actually, you can pump in grout. So actually, you have to, once you have it in place and you reach the desired, once you reach the desired depth, you can actually start the grouting process. And there is a special opening, or access or points where you can actually inject grout behind the shaft. Of course, it's very crucial to have very good contact between the ground and the segment to have a good structural soil interaction, and otherwise you can really create some significant forces if you don't have a good grout or good contact between the soil and the shaft itself. And so basically you can do the grouting, and it's pumped from the surface into certain pipes or tubes that go into the segments. Can we get a copy of the presentation? Yes, I can send you a copy, and please send me an email. My email, I'm not sure if I can, it's mgamal@brileyAssociates.com, so you can send me an email, and I think it's on the it was on the brochure when you joined when you subscribed the webinar. So yes, you can send me an email so I can send it back to you. Okay, that's all I have, and thank you all for your interest in that system. And good luck, and booyah. So now I've concluded the presentation. Okay. You're welcome, and you all have a good afternoon. Okay, bye now.
All right. Okay, thank you so much, Mohammed, for the presentation. We all really appreciate it. And thanks to everyone who took the time to attend. We appreciate your time and attendance. And once again, if you have any questions at all for us, feel free to send us an email at MIDASoft@MIDASuser.com. All right, thanks again, and we hope you have a wonderful day. Bye-bye.